We're going to use a familiar group in our example. We're going to take G to be the symmetric group on 3 objects. So that's got order 3 factorial equals 6. And we've written down the elements of S3 quite a few times now in lectures and in tutorials. So there are 6 elements. There's the identity, which we sometimes denote as E, but since we often use Greek letters for the symmetric group, I'm just for the moment using iota. And then there are 3 transpositions, 3 2 cycles, and there are 2 3 cycles. So that's my group G. And then I need a subgroup of G in order to start talking about cosets. And I'm going to take the cyclic subgroup generated by 1 2. So 1 2 is a 2 cycle, a transposition. It's got order 2, because if I square 1 2, in other words, I do 1 2 and then do it again, I get the identity element. So there are precisely 2 elements in the cyclic subgroup generated by 1 2, namely the identity and 1 2 itself. Okay, and I want to compute the left coset and the right cosets of H in G. So we'll compute the left cosets of H in G and also the right cosets of H in G. So this is an example of computing cosets. And computing the cosets then will give us the cells of the corresponding partitions. We've got 2 partitions. We've got the left partition and the right partition. And in fact, we'll see that those are different in this case. So just remind you, H is the identity element and the transposition 1 2. So what I want to do is compute cosets, and I'm going to do this in a fairly pedestrian way since this is the first example. Later on, when you get used to this, you'll be able to take some shortcuts. So in principle, I can go through the 6 elements of G and compute the coset for each one. So the first element of G, in the order that I listed them, is the identity element. Well, what we're computing here is the cell in which iota lives. Well, since H itself contains iota, the cell in which iota lives is H itself. So we're expecting this to be H itself. But if we were to compute this using the definition, which is that we take H and pre-multiply every element by iota, then of course we get H back. So in a sense, I didn't really need to do that computation, because since this is the cell that contains iota, we know it's got to be H, because H contains iota. And there's only one cell that contains iota because we've got a partition. But what I've done here is gone through the motions of computing the product of every element of H with iota, putting iota on the left. And that's true in any group, any subgroup, that the identity element times the subgroup is the subgroup itself, as you would expect. Now, the next element that we listed in G is 1 2. So what's the left coset corresponding to 1 2? Well, we know the answer to this already as well. Why? Since 1 2 is an element of H, this must be H as well, because we're talking about cells of a partition. There's only one cell that contains 1 2. And since H contains 1 2, the cell containing 1 2 must be H itself. But again, since this is the first example, let's just write this down. So this is 1 2 times H. So I'm really doing an example now of computing left cosets, even though we don't actually need to do this computation. So this is 1, 2 iota one, two, 1, 2. So I'm just putting a 1, 2 in to the left of each of the elements of H, and then I compute 1, 2 times the identity is 1, 2, and 1, 2 times 1, 2 is the identity. So I do indeed get H back as expected. Okay? So the first two elements of G, they're in the order that we listed them, their corresponding coset is just H, as we would have expected, because H is precisely the set containing the first two elements of G. Now, we take an element that we haven't dealt with, which is any of the other four elements. So this is where it starts getting more interesting, because so far we didn't need to do any computations. So let's say now consider, say, 1, 3 in G. What's the left coset that contains 1, 3? Well, we know that's 1, 3 H, which is 1, 3 iota 1, 2. I've just written down H. And this notation just means that we pre-multiply everything in H by 1, 3. Well, 1, 3 times the identity is 1, 3. 1, 3 times 1, 2 is another element of the group which we can compute. And we've done this kind of computation several times, but let's just do it. Where does 1 go? So I'm now doing this computation, this product. This one on the right sends 1 to 2, and the one on the left fixes 2, so 1 ends up going to 2. Where does 2 go? The one on the right sends 2 to 1, and then the one on the left sends 1 to 3, so 2 ends up going to 3. Where does 3 go? The one on the right fixes 3, and the one on the left sends 3 to 1. Okay, so 1, 3 times 1, 2 is 1, 2, 3. So we get those two elements. So that's a subset of G, which in fact is the coset 1, 3 H. And I'm not going to do the computation, but we know that this must be 1, 2, 3 H as well, because 1, 2, 3 lives in this cell. So the coset that contains 1, 2, 3 must be this, because we've got a partition. So I don't need to do that computation. You can check if you want that if you do 1, 2, 3 times each element of H, you will get this back. In fact, you'll get it in the opposite order. Okay, so let's see where we've got to. We now know where 4 of the elements live. But let's just carry on doing the computations. We've got, let's put it on another page. So now consider, we've dealt with the identity, we've dealt with 1, 2, and 1, 3, and 1, 2, 3. So what about 2, 3? The cell that contains 2, 3 is 2, 3 times H. So that's that. So we're just doing the same thing again. So 2, 3 times the identity is 2, 3. And then we can do this. Hope you can all do these computations quite well now using cycle notation. So where does 1 go? 1 goes to 2, which then goes to 3. So 1 goes to 2, which then goes to 3. So 1 goes to 3. Where does 3 go? This takes us 3, and this sends 3 to 2. So 3 goes to 2, and then in fact 2 goes to 1. So that closes that off. Okay? So as we might have expected, the coset that contains 2, 3, in fact contains 2, 3 and the remaining element. So this is also the coset 132H. It must be the coset 132H because the coset 132H is the cell that contains 132, and this does contain 132. Okay? So we've now got our left coset decomposition. So we can draw our bar of chocolate picture. So the left coset partition may be represented as follows. In a picture. So this is a kind of bar of chocolate picture. So we started with S3. That was the big group, that's the big oblong. And then we've got H, which has 2 elements. So that's the subgroup that we started with. That's the subgroup that we started with. And then we've computed cosets. So we computed the first coset was H itself. That's the cell that contains the identity M1, 2. And then we computed 1, 3H. Which turned out to have 1, 3 and 1, 2, 3. So this could also be labelled 1, 2, 3H. So just remember that since cosets are equivalence classes, you can choose more than one representative in general. So each of 1, 3 and 1, 2, 3 are representatives of this equivalence class. We started off with 1, 3, but equally well we could have started off with 1, 2, 3. It doesn't matter which representative we choose. And then there was the final coset which contained the other 2 elements. So this is 2, 3H or 1, 3, 2H. So that's our bar of chocolate picture, or to be more precise, the left coset partition corresponding to the subgroup H. And what we observe here is what's going to be true in general, that each of the cosets has the same number of elements as the original subgroup. So this explicitly shows that 2, which is the order of H, divides the order of S3, which is 6, because we've got 2 plus 2 plus 2. In other words, 3 times 2 equals 6. And that's going to be the general Lagrange's theorem picture. Okay, so that's the left coset partition. What about the right coset partition? Well, you can do the same thing, but now multiplying on the right by your elements. So I'll just leave this as a check for you. And it turns out to be different, but this is a very easy computation. It's very similar to the one we've just done. You're just multiplying on the other side. So to start with, it looks the same. We start off with G, and we start off with the same subgroup. Sorry, my oblongs are getting a bit wobbly, but it's a bit non-oblongy, that. So iota and 1, 2 still live in the same cell. They must live in H. So this H I could also write as the right coset H iota or the right coset H12. I could have written similar things down for the left coset as well. So there's three ways of labelling this: the subgroup itself or either of these two right cosets. And that is the same as the left coset as far as iota and 1, 2 is concerned. But the other two cosets are different. So the coset that contains 1, 3, so this is the coset H13, now contains, as you can check, 1, 3, 2. So in the right partition, 1, 3 lived in the same cell as 1, 3, 2. Whereas before it lived in the same cell as 1, 2, 3. And the other two live together as well. So this is 2, 3 and 1, 2, 3. So I'm leaving you to check this. So H23, that right coset, is the same as H123. So notice that this is a different partition. It's a different way of splitting up the 6 elements from the left coset partition. So what this example shows is that in general, the left coset partition is not the same as the right coset partition. Okay? Now, in fact, it turns out that what's a very interesting case is when the subgroup is such that the left and right coset partitions are the same. And that's a very special kind of subgroup called a normal subgroup. But we are not going to have time to get on to normal subgroups. That will be the start of a second course on group theory. But some groups are very special in that the left coset partition is the same as the right coset partition, and they're called normal subgroups. So this is not a normal subgroup because we've got two different partitions. Okay, well that was an example of a coset decomposition. Now on the worksheet for this week, and in fact 1 or 2 questions for last week as well, you're asked to look at some coset partitions. So there was an example. Notice S3 is non-abelian. If we do an abelian group, then the left and right partitions are going to be equal always, because it doesn't matter if we do the product on the left or on the right. So for abelian groups, the left and right partitions will be the same. But that was a non-abelian example. Okay, well that was an example of computing cosets. Now let's actually prove that what we've seen in this example, that all the cosets have the same number of elements. So this is going to be a lemma for Lagrange's theorem. So we're getting a bit bored of writing this down. Let G be a group, let H be a subgroup of G. Then, no matter which A you take in G, which little a you take in big G, the left coset AH has the same cardinality as H. So all left cosets have the same cardinality of H, and in fact so do all the right cosets. So this is something we saw in the example we've just done. And this shows that the partition that comes from cosets is very regular. All the cells have the same number of elements. That's not true for a general partition. But this is a very regular partition. Well, 2 regular partitions, the left one and the right one. So, what's this lemma saying? Let's just look at the left coset bit. it's saying that the left coset AH has the same cardinality as the original subgroup H. So to prove that, we're going to have to show that two sets have the same cardinality. How do we show that two sets have the same cardinality? Or loosely, the same number of elements? How do we show that two sets have the same cardinality? We've got to construct what? So, in the finite case, we're saying that they've got the same number of elements. Of course, if they were infinite, we've got to be a bit more careful. But so to show that two sets have the same cardinality, we have to construct a what between them? We've got to construct a function which is both an injection and a surjection, a bijection, a one-to-one correspondence. So let's do that. I won't perhaps put in all the details. So let's take an element of G, and we're going to construct a bijection, in other words a one-to-one correspondence, from H onto AH. Doesn't matter which way we go, it's a bijection. Well, in fact, there's a very obvious bijection, there's a very obvious function to write down which turns out to be a bijection. So consider, so let's call it phi. So phi is going to be a function from H, just thinking of this as a set now, the set H into the set AH. So this is one subset of G, and this is another subset of G, possibly the same one, and we're looking at a function from H into AH. And there's a very obvious function to write down. It just takes little h to A times little h. Right? So suppose little h lives in big H, then A times little h will live in A times big H. So this formula does indeed define a function from big H to A times big H. Okay? So this is certainly a function from big H to A times big H, and the claim is, and I'll leave you to prove this, or you can look it up in Fraley, it's fairly straightforward, phi is a bijection. Almost by inspection it's a surjection, because every element of A times big H looks like this. So every element of A times big H is an image of phi, and to show that it's injective you've just got to use left cancellation. I'll leave you to do that or look it up. It's a good exercise in proving that something is a bijection. If you want me to go through that, I can go through it in the tutorial. But it's a very straightforward proof that this is a bijection. And perhaps I should say, similarly, we can do the thing for the right coset. Let's perhaps call that psi, where we take little h to h times a, where the a is on the other side, and that's also a bijection. So phi establishes a one-to-one correspondence between big H, the subgroup, and the coset A times big H, and similarly for the psi. So H, AH, and HA all have the same number of elements. Okay? So I've not completed that proof, I've left a little bit for you. So now we're going to prove Lagrange's theorem. So this is an important theorem, and as I said before, you can tell it's important because it's got a name, Lagrange's theorem. So this is a theorem that you need to know. I won't ask you to prove it, but you should understand the proof. But you certainly need to be able to use it. So, hypotheses. Well, let G be a group, but this time a finite group. And let H be a subgroup of G. So the same hypotheses that we've been dealing with all morning, but we want a finite group this time. And what the conclusion is that the order of H is a divisor of the order of G. So this is our bar of chocolate picture